Object technology. 1. The Unified Modeling Language, UML, is an internationally agreed notation for recording the various elements of an object-oriented analysis and design. The UML defines a number of views of a system through various diagrams such as class and collaboration diagrams. 2. The UML must be augmented with the process to guide the development of the software. In an OOAD, the same modeling concepts are used throughout the software development process. 3. An object-oriented system is characterized as a set of communicating objects. 4. An object is a set of operations together with a state that the object retains between invocations of any of its operations. Transformer operations result in a change to that state while inquiry operations report on the state. 5. An object instance is a particular example of an object from some named class and can be shown in a UML object diagram. A class is a blueprint or template describing an arbitrary number of such instances and is presented in a class diagram. 6. Objects interact through message passing shown in either UML collaboration or sequence diagrams. One object sends another object a message that invokes one of the recipient's operations. The message is bound to the operations definition given in its class or its superclass. 7. Classes may be classified into a hierarchy starting from the general and leading to the more specific. A subclass is a specialization of its immediate superclass. A subclass inherits all the features of its superclass. It may add further features and redefine operations. An instance of a subclass is an instance of its superclass and may substitute at any time for an instance of the latter. 8. Inheritance also gives rise to the notions of polymorphism and dynamic binding. A dynamically bound, polymorphic message sent to an object binds to the operation definition in the class to which the object belongs. Object-oriented analysis and design. 1. The UML is a notation for capturing and presenting the results of an OOAD. To obtain the full leverage of the UML, we must superimpose on it a method. 2. A guiding principle is that an OOAD process should be use case-driven, architecture-centric, iterative and incremental. 3. A use case diagram describes a single task that a system needs to perform. The totality of the individual use cases should describe the full system requirements. 4. Interaction diagrams present a dynamic view of the object instances. They offer a runtime view of the behavior for all or part of the system. 2 kinds of diagram document an interaction: an annotated collaboration diagram and a sequence diagram. 5. An annotated collaboration diagram highlights object structure but can also give the sequence of messages between them. A sequence diagram highlights the time-ordered sequence of messages but does not give information on object structure. 6. An object diagram presents the architectural relationship between objects. It is the same as a collaboration diagram without any messages. 7. An activity diagram is used to show the flow of control among the activities. Activity diagrams can be presented at various levels, as an analysis diagram or as method logic. 8. A class diagram records the classes identified in the problem domain together with the architectural relationships that exist between them. A class symbol is decorated with the class name, the class attributes and the class operations. 9. Relationships between classes include association and composite aggregation. Association should be used where two classes are not conceptually related but within the context of the problem need to make use of each other's services. With composite aggregation, the coupling between the classes is much stronger since the parts cannot exist without their whole. Association and aggregation may have multiplicities recorded in the class diagram. Both may also be labeled with role names. Implementing objects with Java. 1. A Java class is a composite structure in which we can define class attributes, properties, or instance variables and class operations methods. A Java class typically specifies the public services methods and the private representation attributes. 2. The language supports parameterized methods for each class operation. A method body comprises one or more statements. The sentences are assembled into the usual control logic of sequence, selection, and iteration. Statements can create local instances and send messages to objects. 3. A collection object is a container for other objects of some arbitrary class. Java offers several different kinds of standard collections. The nature of the application will usually determine the appropriate container to use. 4. The objects to be contained by a collection will generally have to publicize a mandatory profile including the operations compare to, equals and hashCode. Case study. A library application. 1. The development process revolves around a number of iterations that deliver the final application. The iterations are driven by the use cases identified at each cycle. 2. The application code is realized by successive increments. Each adds a small piece of functionality whose introduction can be tested, thereby reducing the risk posed by new code. 3. The class diagram derived from other UML diagrams developed during the analysis activity acts as the architectural framework on which the application development hangs. The use case iterations and code increments are conducted within that guiding architecture. 4. Each use case is accompanied by a corresponding test case. Further test cases can be introduced to check any special situations that need to be considered. 5. The combined use of iterators and the trio of operations equals, compared to an hashCode makes the code more resilient to change. One collection can substitute for another without code revisions. 6. The domain model should have no responsibility for any input and output. This we achieve by overloading the toString method and by providing non-modifiable iterators. Specialization. 1. A class is a specialization extension of a parent class if it can be considered as an example of a parent. Although the descendant subclass normally has additional behaviors not present in the parent superclass, it must respond to the same messages as the parent. 2. A descendant class has privileged access to its parent through a protected interface. 3. The polymorphic effect permits a message sent through a reference to an object of a parent class to be received and interpreted by an object of a descendant class. 4. An operation may be initially documented as frozen. It is qualified in Java as final, in which case it cannot be redefined by a descendant. This qualification cannot be changed in a descendant class. 5. An operation may be initially documented as polymorphic, in which case its method may be redefined by a descendant. No qualification is required in Java as this is a default behavior. 6. An operation may subsequently be documented as redefined, in which case its method has been redefined by a descendant. It must have been initially documented as polymorphic or deferred and may be subject to further redefinition by other descendants. No qualification is required in Java. 7. An operation may be initially documented as deferred, in which case it must be redefined by a descendant if its class is to be concrete. It is polymorphic by implication and may be subject to further redefinition by other descendants. It is qualified in Java as abstract, and the class to which it belongs must also be qualified as abstract. 8. An abstract class can have no instances but acts only to define the protocol of its descendants. It may have some of its methods defined. 9. An interface class can have no instances but acts only to define all or part of the interface of its descendants. None of its methods are defined. A class that implements an interface must define its inherited methods or it is itself abstract. Case study. The library application revisited. 1. Scenarios represent different paths through a use case. Scenarios have basic and alternate flow of events through a use case. 2. Use cases can have include relationships and extend relationships. They simplify use cases by sharing some common functionality. 3. Specialization and the use of the polymorphic effect can radically simplify our designs and implementation code. The code is expressed in terms of abstract superclasses rather than specific concrete classes. 4. The full power of the object-oriented paradigm lets our designs accommodate new requirements without the necessity for substantial changes. 5. The full power of the object-oriented paradigm includes class specialization, object substitution, the polymorphic effect, and designs expressed in terms of interfaces. 6. An architectural framework is a general solution that can be instantiated for a particular domain-specific application. 7. A persistence mechanism provides data storage between separate executions of an application. Object serialization in Java is a mechanism for saving the state of an object as a byte sequence and from which the object state can be restored. Graphical user interfaces. 1. The abstract class component is the root class for many of the graphic components. 2. Components can include other subcomponents in a parent. Child arrangement. A layout manager is responsible for positioning the children of a parent component. 3. The model view controller design pattern is a significant feature of the architecture of the swing classes. The view controller is responsible for the presentation and the interaction with a graphical component. The model element represents the state information for the component. 4. Events in Swing are represented by objects of different event classes. When an event occurs, an event object is passed to an event handler. The event object carries the data associated with the event. 5. The Java event model is based on the notion of event listeners. When an event is generated by an event source, the source notifies all its listener objects by calling a fixed method and passing to it the appropriate event object. For the source to be able to call a specific method in a listener object, the listener object must implement a particular method protocol as defined by a corresponding listener interface. 6. Inner classes are frequently used to realize event listeners. Design patterns. 1. Patterns are ways to describe best practices, good designs, and capture experience in a way that it is possible for others to reuse this experience. 2. Specialization and delegation are widely used in object-oriented systems. Both provide powerful ways of reusing code. Delegation can often be used in place of specialization, offering flexibility at runtime. 3. The use of interfaces can increase the flexibility we seek. An interface provides only a specification of its services. In order to conform to an interface, a class must implement all of its services, i.e., supply a method body for each operation. Crucially, the classes can belong to different class hierarchies. 4. The adapter design pattern is used to introduce a class with a required set of services that is realized by another class that has the wrong set of services for a client. 5. The singleton design pattern guarantees that no more than one instance of a particular class exists in a program. The singleton also offers a common point of access to the object throughout the application. 6. The visitor pattern is used to separate the code to traverse a possible complex structure of objects from the processing that is performed against each object. 7. The template method pattern lets us fix the ordering of steps in an algorithm but lets subclasses vary the details of the separate steps. 8. The abstract factory method delegates the construction of concrete class objects to an appropriate subclass. This way the client code need not know what actual concrete object it references. 9. The decorator pattern is used to dynamically add new functionality to an object. 10. Many of these design patterns have been incorporated into the Java API. Case study. A final review. 1. Refactoring is often necessary as part of a final review. Although refactoring depends on experience, the subject has been well documented and a vocabulary exists to describe a sequence of refactorings that might be applied to a system. 2. Each refactoring should make a relatively small change. It should be accompanied with extensive testing to guarantee the same behavior from the software. 3. Redistribution of classes in stereotyped packages clarifies their role and eases the maintenance burden. 4. Code duplication is a major cause for refactoring. 5. Exposure to design patterns can help identify useful refactorings. And finally, this book has been concerned with object-oriented design, the unified modeling language in the Java programming language. Throughout we have stressed the importance of conducting an OOAD prior to the implementation of a system. We have used the UML to enhance our understanding of the system by documenting different views of it. In our opinion, this brings a significant measure of quality to the final program code. From Chapter 2 we have argued that system development should be architecture-centric, employ an iterative approach and be use case-led. A lightweight life cycle was introduced to bring discipline to development activities without being encumbered by needless bureaucracy. The expressive power of the UML has been crucial to the success of our designs. Its various diagrams gave important insights into the final system. For example, a sequence diagram reveals how message propagation through a collection of objects implements some part of its functionality. Often the diagram can be mapped directly into code. Of all of the UML diagrams available, the class diagram has been the most important. It is central to the modeling activity as it defines the architecture we realize in code. In effect, it drives our implementation development. We seek to forward engineer the program code from the class diagram. The class diagram reveals association and aggregation relations that exist between classes. This led to the use of the Java collections framework. As well as acting as an exemplar of OOAD, their use markedly simplified our application code. Specialization hierarchies are also documented in a class diagram. They helped us make use of the polymorphic effect and to aspire to design to an interface wherever possible. Ultimately, this led to the development of a framework. The more sophisticated applications of polymorphic substitution gave rise to advanced design patterns. They offer elegant solutions to many common design and programming problems. The vocabulary they introduce elevates the level of abstraction we can achieve in our designs above that of an ordinary class diagram. Our discussion of design patterns led naturally to refactoring our designs. Jointly, refactoring and design patterns represent leading-edge developments in object orientation. Object